Okay, hello everyone. Welcome to this session on a contributor's guide to Parsec. It's great to be here at Connect. I'm happy to be able to give you this introduction to Parsec and not just an introduction, but an invitation, in fact, to this open source initiative. I've just realized I'm not sharing my camera. Just a moment. An invitation to this open source initiative, which is at an exciting stage in its evolution. I'm hoping we'll transfer some of that excitement to you in this session. So let's introduce ourselves. I'm Paul Howard, and I'm joined by my colleague Hugues de Vallon. We're both at ARM, both working on Parsec. You can see our email addresses, GitHub handles there. And we're part of a broader community of Parsec maintainers and collaborators, both inside and outside of ARM. And we'll be introducing that community to you as part of this talk. Okay, moving on, agenda. The title of our talk is A Contributor's Guide to Parsec. So our main aim is to get you interested and enthused about contributing. But Parsec, it might not be familiar to you. So if it's not, I'll begin with some scene setting. We'll cover what Parsec is, the problem that it's trying to solve, and we're going to spend some time also talking about the Rust programming language, which we're using in Parsec. We'll introduce Rust quickly for those who aren't already familiar with it. We'll talk about why that language choice is important for Parsec and for ARM, and then we'll talk about the opportunities that exist within Parsec for getting involved. And then we'll wrap up by giving you some links, some pointers that you'll need to start that journey towards becoming a member of this growing community. It is a short session, it's quite a crammed session. We may have a few minutes at the end for questions. Apologies in advance, we might not get to questions that come in over live chat, just because of how crammed the session is. But if you post your question on the conference Slack channel, so the LVC20 116 channel, Hugues and I will certainly get to it afterwards. All right, let's start with the why. So why Parsec? Now, first we need to realize that the world of edge compute is changing. It's no longer just a world of gateways, of protocol translation. It's becoming a much richer, a more compute-capable world. So it's a place where we want to execute workloads for things like machine learning, sensor fusion. It really makes sense to do that kind of compute close to our IoT devices geographically, because that's where the data is. So these kinds of workloads are migrating out from the central cloud to the edge. Now this creates a conflict, and the conflict is between the need for those workloads to be easily deployed and the need for them to be highly secure. So as we move from the managed data center to the edge of the network, our threat landscape changes. So too does the diversity of platforms. So we have different chip architectures prevalent, different roots of trust, different kinds of hardware for key storage, and correspondingly different specs and APIs that we need to comprehend and consume and code against to ensure the security of our private keys and hence of our workloads at the edge. But for ease of deployment, we want to retain that fluid cloud-native delivery experience, which means staying highly decoupled, actually, from those platform details. So we want the best protection for our confidential secrets, but without coding in all of that highly specialized knowledge. It's a bit of a paradox, and it's a paradox that Parsec aims to solve. Parsec gives us the platform abstraction for security. It brings us this uniform compatibility across a diverse world of edge, runs on any architecture, can handle the details of hardware security, whether that's provided by trusted platform modules, hardware security modules, trusted applications, or other kinds of roots of trust. And it provides a common API that can be consumed into any programming language, nicely decoupled, easily deployed in cloud native workloads. So that's the what. Let's see how it does that. But here's a layered model of Parsec. Platform agnostic security begins with some kind of API, and Parsec's API is rooted in platform security architecture, or PSA. The PSA is a holistic security offering for IoT and includes a suite of developer APIs that are agnostic, strongly specified, algorithmically agile, and perfectly suited to having different kinds of hardware backend. Now, the PSA Crypto API offers functions for key storage and cryptography, but it was designed for embedded programming in constrained single process environments. So part of Parsec's job is to transform this core API into a cloud-native developer experience in this rich application class world. Now, it does this by creating a service, the Parsec service, and this is a user space daemon that can be called by multiple client applications in a rich OS environment. And those applications needn't be written in C. The Parsec service re-expresses that API in a language-neutral way using a wire protocol. And Parsec builds on this still further with client libraries which understand that wire protocol and then prevent a very convenient, fluent coding surface to application developers. And with that conceptual model in mind, here's the service architecture. Here's how it looks. And imagine that everything here is running on an edge node with a rich OS. You can see the Parsec service there, which represents the underlying hardware, acts as a broker for access to it. The Parsec service is organized as a front-end, back-end architecture, where the front end is a listener that provides a service endpoint and implements the IPC wire protocol that I talked about. And this is where we receive API calls from clients. And then in the middle, we have some access control logic, where we make sure that multiple clients have key stores that stay isolated from each other. And then back-end modules, which we call providers, is where we isolate all of that platform-specific knowledge. So this is where we would have code that specifically knows how to talk to, say, a TPM, an HSM, or maybe services running in a T. And then on the application side of the wire, over on the left, we have a client library, which talks to the Parsec wire protocol. And then lastly, what the application sees is precisely that convenient developer experience that we said we wanted. So it's built around a standard set of PSA primitives, but then honed and refined to provide a fluent and simplified experience. And that is the Parsec Vision, open initiative to provide convenient access to the secure facilities of any platform to multiple client workloads in any programming language. So when we talk about contributing to Parsec, we're talking about contributing to this vision. And let me at this point hand over to my co-presenter. So I'll hand over to Hugues now. He's going to talk a bit about Rust, which we're using extensively in the project. So go for it, Hugues.
Thanks, Paul. Rust is a programming language that we choose for Parsec. We thought it was a perfect fit for Parsec, and is also a programming language that is really important for ARM today. Let's see why. So today, ARM is everywhere, from deeply embedded systems, running bare metal code, consuming very low resources, through application processors, running, for example, Linux, even up to supercomputers, ARM is everywhere. And on those different domains, safety and security is important. A popular figure is the number of CVEs in the Linux kernel, and more specifically, the type of those CVEs. It was shown that in 2018, 70% of those CVEs were due to memory safety bugs. For example, some of those, like buffer overflow. As new software appears, code bases gets bigger and bigger. Software gets more and more complex, and this won't go down, especially adding more and more parallelism to your code. But making software safe and secure is a really hard problem. It needs experience. One needs to know when your code is safe and when it is not. It needs discipline to put in place strong practices so that reviews are done to make sure that the code is safe and the appropriate tooling are used. And money to train the engineers for those safety problems and also to buy the necessary tools. ARM is constantly seeking innovative ways to improve those things. And for this specific domain, Rust ticks a lot of boxes. It was, especially for Parsec, a very good choice, as Parsec is deeply linked to security, and that safety there is a big problem. So let's see why Rust ticks a lot of those boxes. On the next slide. Yes, thanks. So for 4 principal reasons. First one is safety. Rust has a rich type system with really strict and strong types. It has these specific features of ownership, which eliminates at compile time. So it's very specific because it's at compile time. Most data races bugs due to thread safety and memory safety. So all sorts of common CVs are eliminated at compile time. In terms of performance, Rust offers native compilation, no garbage collection, no managed runtime, low-cost abstraction, and it can run on embedded and bare metal. As Rust has LLVM as its backend, any target that can run on LLVM can easily be added to Rust. Also, it has a very nice interoperability with C. For two main points, it is really easy to call from Rust a C API going through the C4 function interface. And it is really easy to automatically generate Rust API from a C header file. In terms of tooling, Rust is known to have a very steep learning curve, but the compiler helps you. The messages thrown by the compiler are friendly, easy to understand. Most of the Rust libraries have great documentation. It has a very nice tool called Cargo, which is an integrated build, run, and test system. It has an integrated package manager where people can upstream their Rust libraries called crates. And included in the toolchain that you download with Rust, there is a static analysis tool and a style formatting tools. And lastly, expressiveness. Rust is heavily influenced by other languages, some of them from the functional programming languages area. So it has features like iterators, closures, generators, pattern matching, destructurings, and more. That promotes readable and maintainable code. And on that last point, and with all the safety, performance, tooling, and expressiveness, it really makes Rust the perfect language for safe open source code because it increased the general level of code quality that anybody can produce. So what is ARM doing to help the Rust community? If we check on this slide, the main thing that ARM is doing right now is helping to make AR64 on Linux a tier 1 Rust target. That is the highest level of support for a Rust target. RFC is open, and you can check it out for details. ARM is also having close collaboration with the Rust core team. So on that topic of having the AR64 Linux target, there is a creation of a CI infrastructure that is running the Rust compiler test directly on AR64 Silicon, instead, for example, of being simulated on x86. And specific tests are being maintained and improving to improve the support of Rust on AR64. We're also working on extending Rust to use AR64 advanced Neon and SCMD interstrings, and also to add the support for ARMv8m just done features in Rust. In Parsec specifically, we are helping the Rust community by publishing helpful crates and contributing. So for example, we published Rust abstraction for a TPM API, so to communicate with the TPM with Rust, and for PAC cryptographic APIs. We also contributed to PKCS11 crates, crates providing ASN1 types, and also bindgen, which is a tool I talked about that automatically generates the Rust API from a C header file. So really think that we really thought that Rust was the perfect choice. We are really happy of working with it so far and really look forward of contributing more with the Rust community. I'll let Paul continue with the next slide.
Thanks, Hugues. And I'll hand back to Hugues in just a second, where he's going to talk about some contribution opportunities in Parsec. But first of all, I just want to emphasize as a kind of prelude to that Parsec is really poised for growth right now. It's at an ideal stage in its life cycle where there are opportunities not just to get involved, but to influence future direction, form special interest groups, to take ownership of key pieces of that vision. And earlier this year, we got accepted into the sandbox stage of Cloud Native Compute Foundation, which was a great step forward. So the project's fully public, it follows the CNCF's IP policy and its code of conduct. And it's starting to get used too. So ARM's Pelion device manager client, for instance, now has got an option to use Parsec to manage the device identity key pair for registering to Pelion cloud services. And we're also working with Red Hat on a demo that's based on integrating Dbus and Network Manager with Parsec And that's something you can look out for at ARM Dev Summit next month. And with that, I'm going to hand back to Hugues.
Thanks. So in terms of contribution pathways, we selected 4 specific areas where it would be possible for anyone to contribute, but more than that, to own the specific piece and help us maintaining them long term. The first one is creating new hardware firmware integration. So the way that Parsec is currently communicating with the different crypto modules that we support is through provider modules. So we currently have support for the TPM, for PKCS11, and for the embed crypto software library. But we would really like to add more support for other crypto modules, such as custom secure elements, cloud HSM, or ARMv8 trusted word applications. And for those specific modules, we would welcome anyone to discuss with us about how it will be possible to add them with the Parsec code base. That would allow platforms having those modules to be able to run Parsec. The second contribution pathway is about addressing functional gap to enable use cases. So when Parsec was started, the first use case that was implemented among the multiple providers that we support is for asymmetric signing and verifying, where a key pair can be generated inside a TPM or inside a HSM. It can be used to sign a buffer, and the public key can be exported for someone else to verify the signature. This was the first use case that Parsec would be used for, and we implemented those things first. And mostly for asymmetric signing and verifying, it was for the RSA algorithm. But we would like to expand our coverage and ultimately to have almost all of the PAC crypto operation implemented. So that is, for the one that we currently support, adding more key types. So for example, as well as supporting RSA keys, also supporting elliptic curve keys, and also adding more operations, for example, supporting the MAC operations. And those for all of our providers. So those are specific items which would be really easy for anyone to contribute and help us improving the coverage. The third contribution pathway is on the client side. Parsec is pretty much a Rust shop. So when we started Parsec, the first client that we did was naturally the Rust client. It allows you to access all of the Parsec operation with Rust, but without this great developer experience that was taught us, without this idiomatic Rust usage. And similarly for all of the other clients that we would like to add in Parsec, a Go one, C++, Python, or Java client, we would like to have people that know this language and that know the cryptographic library in this language in order to help us to build very nice and idiomatic client libraries in those languages. So that is both for people that would like to build from scratch those libraries, and for people that know specific famous cryptographic libraries in those language to perhaps build a Parsec backend to this library, so that it would be possible for a crypto library that was software only before to use Parsec in order to, for example, store RSA key in a TPM, all that using Parsec. Lastly, the final contribution pathway we're looking at is about expanding deployment horizons. First, in terms of environment, currently, Parsec and its clients are working on the same operating system, on the same host, where Parsec clients are different Unix processes communicating to the service. We would like to have more environments for them to be virtual machines or containers, where different clients could be in different virtual machines or in different containers. That would need some work and some more design to make it work with the Parsec service. In terms of operating system, we're currently only supporting Linux, but we like to add the support for Windows and other real-time operating systems. For orchestration, and that has to do mainly with the identity provider part. So the way that Parsec can partitionate its key store so that each client can have access to only their keys and not the other ones is by giving to each client a specific identity, a unique identity that is trusted by the Parsec service. In order to make this work for the different environments that we want to support, so for different containers or different virtual machine, there is some work needed in terms of how to set a specific identity for those different workloads and how to manage and verify it. And lastly, the ecosystem. The ultimate goal of Parsec is to be deployed in all locations possible. So we'd like to identify use cases and integration points where we need to identify to enable Parsec on them. So that's all for the all possible contribution pathways. If you're interested in one of them, or you would like to know more about Parsec, if you'd like to join the Parsec community, you can access all of our code on all of our repositories at the Parallax second organization, which link is written here. You can also access our technical documentation on the Parsec book. To talk to us directly, we are on the Parsec Slack channel on the Docker community Slack workspace. And we are also holding meetings every other Tuesday at 4:30 p.m. UK, when you can directly talk to us, or if you have a specific topic that you would like to address more in depth, you can also come and we can discuss that. Thanks a lot for listening to me. I hope I got you interested, and I'll give it back to Paul to conclude.
Fantastic. Thanks, Hugues. Thanks, everyone, for listening. So that's the end of our session, and I hope we've succeeded in giving you a flavor of what Parsec is, what the contribution opportunities are. And as Hugues says, if you're interested, you want to take it further, do please come and join us on that Slack or in our Tuesday meetings. We're going to make you very welcome. If you have immediate questions burning in your mind right now, and you want to come and chat with Hugues and me during the Linaro conference, there's also a channel on Linaro Connect Slack, LVC20-116. We'll be hanging out there. You can come and chat with us while the conference is open, and we'd love to hear from you. Thanks for having us. Thank you, Christine, and the organizers. Thanks to everyone for listening. Have a great day and a great rest of the conference. All the best.